Welcome to this video on oscillatory motion. In this video we're going to be taking a look at a kind of motion that occurs in nature where an object has some sort of repetitive or sometimes described as periodic behavior. So over here I have a simulator opened up from the fet.colorado.edu website. There's a link in the description below. And what we're going to do here is take a look at this pendulum. Now a pendulum is a string of some kind, usually with a mass attached at the end, and the mass is referred to as a pendulum bob, spelled like the name. And we'll also take a look at later videos at a physical pendulum, and that's a pendulum where the mass of the string, or the mass of the thing that's connecting it to the rotating point, actually does factor in. So in this case, because of the string has such a low mass compared to this mass at the end, we really don't have to incorporate the string's mass into the situation. So it's not a poor example or an example that doesn't actually exist realistically. You can do this in reality and not include the mass of the string because the mass is so light compared to this. So here, if we pull the pendulum back, let's pull it to about 30 degrees here, and we let it go, we see that it rotates back and forth, or swings back and forth, through this dashed line, which is referred to as the equilibrium position. Now, the distance that it reaches on either side, okay, is referred to as the amplitude of the motion. Now, we will see that there's other kinds of amplitude as well. This is going to be a position amplitude. There can also be velocity and acceleration amplitude, and that's just a maximum position value. We oftentimes will refer to that as x sub m or x sub a or any other kind of designation to show that it's specifically the greatest position that it can reach. Now, we refer to this kind of oscillatory motion as periodic motion, and periodic motion is the term that describes this repetitive behavior. So when we put this term here, periodic, we're oftentimes referring to it as repetitive behavior. Now, it's not just any kind of repetitive behavior, it's specifically behavior that is moving around some sort of equilibrium. So it wouldn't be the same as, an object that keeps repeating the same motion as it moves in a straight line. It could, but it doesn't necessarily have to do this. So we see here it's swinging back and forth between these two positions through the equilibrium position. And the time that it takes to go from, let's say, this amplitude all the way through and back to that amplitude is considered to be one complete cycle, which takes a certain amount of time, referred to as the period. So the period is the amount of time in seconds to make one cycle. Okay, so that's the period amount of time to make one cycle. Okay, so you can either say from equilibrium, through equilibrium, and back to equilibrium, or you can say from an amplitude position to the other side and back to that amplitude position. So any repeating place passing through the equilibrium will be the period. Now, another way that we can measure the period is an indirect way by measuring what we refer to as the frequency. So oftentimes it's really hard to time the time it takes to make one cycle because your reaction time is maybe not quick enough. But what you can do is you can count the number of cycles in a given amount of time, and that could be any amount of time that you decide on, and then you would know the frequency of this motion. So for instance, if this little pendulum bob had 20 complete cycles and that took 10 seconds to occur, that would say that the frequency is 2 seconds to the negative first, because the second is down here, which is referred to as a hertz, Hc. So 2 hertz, and if I think of that, that's telling me that it does 2 cycles every second. Now, it hasn't told me how long it takes to make one cycle. That's indirectly connected. So what I can do then is say that the inverse of the frequency will give me the period. Because if you can do 2 cycles every second, it takes half a second to make 1 complete cycle. And so that's how the period and the frequency are connected to one another. So far we have the amplitude, how far it's moving on either side, so its maximum displacement from equilibrium. We have the time it takes, the period, to make 1 complete cycle passing through equilibrium, and we have the frequency. The last thing we're going to look at in this particular video is this idea of what's known as a restoring force. A restoring force is particular to this kind of motion. Now, if I pull this pendulum bob up this way, and then I hit the play button here, I see that when it reaches its maximum amplitude, it's returning back to the place that it was before. Now, what we can do here is, as we look at this, is we can see that the restoring force must be pulling it back, and so it's changing direction, the restoring forces. So here the restoring force is most likely gravity, because what that's showing us is that whenever it reaches some position that's not equilibrium, the restoring force tries to take it back to equilibrium. So it's referred to as a restoring force because it tries to restore equilibrium. Now the restoring force always pulls back in the opposite direction to the displacement. So one generic form of writing this is what we looked at before as Hooke's law. So it says that the force is equal to the negative times some constant times displacement. So if I displace it more, it pulls back more. So the restoring force, and we could refer to this as F sub R or F sub S or however you want to designate it. Now there's an important distinction to know about restoring forces. If the restoring force is linear, or it's directly proportional to the distance of displacement, or the angle of displacement, then this particular kind of oscillatory motion is referred to as simple harmonic motion. Simple harmonic motion is only true if there's a linear restoring force. That's simple harmonic motion is a kind of oscillatory motion. So all simple harmonic motion is oscillatory motion, but not all oscillatory motion is simple harmonic motion. For example, if you have a restoring force that is equal to, let's say, we'll make K 1/2, let's say. So K is 1/2, and this is going to be X to the 3/2. Now this is no longer a linear relationship between these two. And because of that, the restoring force then is not causing simple harmonic motion, but it still is oscillatory motion. This just means that the value of the restoring force is not linear or not directly proportional. So keep that in mind. Not all oscillatory motion is simple harmonic, but all simple harmonic motion is oscillatory. Now we can visualize the motion here by graphing the position as a function of time, and we can show that over time, let's say we start at equilibrium, over time we have a positive maximum displacement, and then we have a positive or a negative maximum displacement, positive and then a negative. And so oftentimes graphically we will show this as a trig function that will show us a motion that is oscillatory or simple harmonic. Now this over here is the amplitude. Okay, so that would describe the amplitude, and this particularly is the position amplitude. Okay, and we could see here now that the maximum velocity is occurring when the derivative of this graph is its maximum. So positions like right here, right here, right here. Its minimum is occurring over here because the derivative at those positions is just equal to 0. Okay, so we can see that the velocity amplitude is occurring at this position when it's passing through equilibrium. Okay, so that's the highest velocity that it will ever be. and we can also take a look at that by actually graphing the function. The period or the frequency can also be seen in this graph visually. So from any one place to the next repeating place, which would be right here, the time that it takes for that to occur is a period. And we'll oftentimes refer to the length of this, so not the length of time, but the length in meters, as the wavelength. Because this is oftentimes referred to as a wave, or this could be the distance of the cycle. Alright, so one complete revolution, or 2 pi radians, would be how we could describe it in radians. So if we're going to write out our full trig function here, we can think about all the parts of that generic trig function that could relate to the period, the wavelength, the frequency, the amplitude, and we'll take a look at that in the next video.